Okay, so previous step we had the supernatant, which is after this centrifugation. So we have a lot of different proteins in this supernatant now. And then the next step is salting out, actually. The salting out I explained before that we will put ammonium sulfate, which is this ammonium ion and sulfate ion will take a lot of water molecules so that among the protein population, the protein that has a low solubility will be precipitated first. So that is basically you're taking out of the low solubility proteins out of the system, which is quite a high amount, about 50% powder into the protein solution. So the important thing is don't put it all of this ammonium sulfate at a time. That will this all step has to be a thermodynamic step. So that means we have step-by-step additions of a salt. So that will take a time for the added salt in solution. That will have the amount of water molecules will take it out from the system. That will take a time, and then you put another amount of the additional amount of this ammonium sulfate. And then they will take water molecules from the protein to the added salt. So that repeating this process. So don't put it all at a time. So then now you have after the sodium ammonium sulfate addition, proteins with a low solubility will precipitate it out. You will see basically not a precipitation, but you see actually this overall solution is crowded. So it's clouded, so that clouding precipitated like complex will be separated by the centrifugation of 15,000 RPM for the 15 minutes. So then after this step, you will have basically very highly water soluble protein, which is the case of this PYP, this protein that is a relatively high solubility in the system. And then anyway, you have to put this ammonium sulfate ion have to remove, so that you have to remove the performed by dialysis, that is semi-permeable membrane with a molecular weight cutoff. So that cutoff should be higher than the ammonium sulfate, which has to be 2K to 1,000 kilodalton. Above than that, any membrane cutoff is fine. So that during the dialysis, the solution volume is largely increased. That means the inside of this membrane has high salt. Outside will be the water. So the water comes in because to dilute overall system, and salt is coming out. So that the initial volume is about this much. Then because water is keep coming through this membrane, that volume is increased. So that is about 2 times or 3 times increased. So imagine that we actually dealing with about 1 liter culture of the E. coli that we add about 15 milliliters of this volume, and then we might have about this volume range. You might have calculating after this dialysis step to increase the volume. That would be 30 or 45, so they have to be increased. Otherwise, the membrane will be bursted because of the incoming water molecules. So now is this PYP purifying. This is an ion exchange column. So this has no histidine tag cases. Later on, you have another step is the histidine tag purification. So this is the separating two directions. So that you have now salting out product, which is fairly already purified protein solution of the highly soluble proteins, including the target protein. But there are others also proteins are there. But there will be without histidine tag pathway or with histidine tag pathway. We have 2 different pathways I will explain. Okay, this is one of it. This is not a sequential this by this after this step we perform this step. No, this is not that case. You have the one step and the other step that is parallelly you can choose either way, plan A or plan B. So this plan A is number 1, has no histidine tag step, so we running ion exchange column. So now, the previous step, we had a dialysis of the solution, and the PYP, the target protein, is inside this bag. And then, as I mentioned before, this volume is increased. 15 milliliter becomes a 30 or 45. So to handle properly, you have to reconcentrate the solution again. So they concentrate the PYP solution to around 5 to 10 milliliters by using a filter that is molecular weight cutoff. This is cutoff size. It's about this size. So then, the molecular weight of PYP is above 10,000 kilodalton. So then its membrane molecular weight above the 10,000 will be remain on top, and then anything that has lower than 10,000 will be down. So you centrifuge it. You centrifuge by this about 3,000 RPM. And then water also, of course, the water comes. If this is the membrane, water goes down. And then they concentrate it of the overall solution. Also, the molecule that has lower cutoff size, smaller than this cutoff size, will be also going down. But the overall purpose is concentration, so that you decrease the volume from about 45 milliliters down to the 5 to 10 milliliters to handle properly. So after this, you end up with the solution with about this small volume. And then that volume is loaded to ion exchange column. It's the resin we particularly use, Cephirose resin. So imagine that you have a column that I showed you before in previous class, and then you load it to the protein solution, and then the proteins will be adsorbed on top through this resin. And then the solution now, proteins will bound to the column overall, and then you wash a little bit, a weakly bound protein, washing buffer, the same as the tris buffer with the sodium chloride on. So then after this you have the fraction collector is because we have the sodium chloride solutions will going down, and then the bottom you have collectors are rotating. So you have about this number of the tube, you put it there, and then every time, maybe 5 minutes or 1 minute, then they rotate it that time, and then the protein solutions will elute it by the gradient of the sodium chloride. They will elute the protein. And anyway, we don't know which proteins are in the tube, but anyway, proteins are separated into from the ion exchange column as the sodium chloride increased, and then proteins are eluted as sequentially based on weakly bound protein eluted first, and then strongly bound protein eluted later. So that is the things. So then to do this, the gradient mixer, because one line is, you have a column, you have two lines. One is the 0 molar of the sodium chloride, the other one is high molar, several molar of the sodium chloride. So the gradient mixer you open, so the gradient solutions, now the two solutions are mixed. So depending on how you open those two lines, and then you can change the concentration of the sodium chloride. So that is basically you increasing the direction. So the protein will be washed off faster and faster. So during the washing procedure, make sure that the solution is in the inner and outer layers at the same levels that the solutions was stirred at high levels. So anyway, you have the about this number of the tubing with each tube has a certain amount of the solutions are there, and proteins are our target protein that we want to purify is some belongs into some tube in there. So this case is we set about 2 minutes per tube. So one tube is waiting for 2 minutes, and then after 2 minutes they rotate it, the second tube is coming. So then after this we have among this number of the tubing, you have which tube has protein, which is a PYP cases there. So we can see, because it's a yellow protein, so that we have purity index for each fractions, and the yellow proteins that has absorption of the visible range, absorption about 446 nanometer. So this is the things that we want to purify. This is the evidence of this tubing has a protein of the target. So we measure this of each tubing, and then with this higher number of this index, which is also every protein has a 280 nanometers, which is a tyrosine and tryptophan. And then this index is becoming lower than 0.5. This is a practical number, it's not important, but that means it's a lower, the better, because this PYP specific signal is higher at a given protein there. So then higher becomes this index is overall lower. So then, so we take certain fractions of the tubing with this index of 280 divided by 446, about this number, we'll take it. So that is the all procedures of the first. That column has histidine tag without cases. Okay. So the second case now, second case is you have histidine tag cases. So now still you have to remember that you have a salting out procedure, and then the salting out procedure you concentrate it because salt is coming in, you concentrate it, and then now that solution, so now you prepare basically several buffers. So that is equilibrium buffer, sodium phosphate, pH 7, washing buffer number 2. So basically what is this difference is the sodium chloride concentration is different. And then it becomes higher and it's the same, but now you have a 2 millimolar imidazole. That's, remember that the previous class we have a histidine tag has how we elute it, lowering pH, or you adding the imidazole. That is, imidazole is a side chain of the histidine that is replacing of the histidine tag binding. So basically you add a lot of histidine side chain amino acid there. So actually you elute it from this column that is tightly bounded by affinity column. Then you add this amount of higher concentration of imidazole solutions. That is how all this procedure, protein adsorb on nickel histidine column. Basically you add these solutions, you wash it, everything, except for the PYP that has actually histidine tag. That tag is bound to this histidine tag column, NTA column. And now you add this concentration of imidazole, you added this imidazole, and then this tag is now eluted basically at this elution buffer. That's why you have to prepare several buffers there. So the actual procedure, packing the resin inside the column. So it's like a GPC resin that I showed you before. Remember that I added powder, then you put the water and then they swell, becomes like that resin. And similar procedures that I here. And then that resin is equilibrated with the solutions with basically this solution, sodium phosphate buffer pH 7. And then now pour the PYP solution. Pour the PYP solution. It's now a mixture of the protein, and then all proteins are bind, and then simply washing, because the proteins, our target protein bound, also the protein without the tag will be eluted automatically, because this is a histidine column system. But still, histidine column has a charge, because nickel is charged, and nickel is positive charge, and then some proteins will have a negative charge will bound to it, is possible. So then we wash by the sodium chloride of the buffer that I explained here. So we wash number 1 and number 2 solution, and then also number 3 solution. and then we assume that the proteins, our target proteins, is still bound in the resin, the column resin. And then now we add the solution buffer, the 200 millimolar imidazole solution containing solution. Then we add to this PYP bound column, and then we elute this column, and then the monitor, the PI, this is a purity index. Purity index here means I gave this indexes before. So then, so that means we have some certain fractions that still be collected, even eluted. As soon as you elute it, you pour the elution buffer. That doesn't mean that inside in here we actually immediately get PYP. Is not. I mean, you actually pour the solution. If this is the size of the column, and the imidazole solutions goes in here and slowly, very slowly. So you don't know which fractions will come in. So then still you have to get a fractions preparing several number of the tube, and then you got tubing number 1 and number 2, number 3. Probably first several tubing doesn't have any target protein because you start adding the elution buffer. So, but at the same, finally, an elution buffer goes through this column, and then that will coming PYP is target proteins coming out. So then you still have to be monitor purity index in this case. So anyway, so you basically collected it with a high purity, low purity index solution, and then you take it. So now we have to do dialysis. The reason is basically you added for elution. In this case, you have 200 millimolar imidazole molecules in solution. But this is a small molecule. It's a 5-member ring molecule. Has to be removed from this system. So that's why we perform the dialysis. The small molecule comes, the water is coming by exchanging the solution. So the outside in this case was a 20 millimolar tris with the salt and pH 8.5. There's a reason why. I will explain later. And this step is for the enzymatic cleavage of histidine tag, because remember that I had explanations of the histidine tag and then enterokinase, right? So I explained enterokinase when I explained affinity column procedures. If you forgot that part, it's better go back to the protein purification part number 3. So I already explained that part there. So anyway, you have to do that cleavage experiment. You need some tris buffer there. So then that's why you have to change sodium phosphate buffer basis system to tris buffer systems. And then also you remove the imidazole solutions. So now that's why histidine tag cleavage. Now is you have a PYP is a target protein, and there's a tag. You put enterokinase. Basically you cleave it, and then you will purify this one. So so now you did dialysis. You did dialysis here. So then that means your imidazole comes and water molecules goes in. Your overall volume will be increased. So you have concentrate again. So the concentrated about 5 milliliters. So and then you put enterokinase there, and then enterokinase, and wait for 3 hours, and then put additional enterokinase and wait until at the 37 degree. Now this time you have target protein and tag will be cleaved. But now you have to think about the two things. If this enterokinase reaction is partly working, that means you have 100 molecules of this protein. Say this enterokinase may be 90% cleaved, but still you have a 10% uncleaved. So you have to purify it again, right? So it's easy because if you have another nickel NTA affinity resin same, so that you can actually easily purify, because enterokinase uncleaved, which is this one, total length, will bound again to this column. However, if they cleave it, then there's no histidine for this protein. So they elute it through this column without binding this resin. So that's why you can actually purify, distinguish between unreacted portion and the reacted portion. So then transfer this reaction solution to this NTA resin, and then collect. That's why this is important. Flows through PYP, because that means it's cleaved and no histidine tag, they flow through this column. Okay, so then you collected that one. Okay, if the cleavage reaction can be very low, depending on there's no reason why, but still very low, then anyway you have to repeat this process again. And then you collect the first fractions and the second fractions again, and then goes to the next step. Okay. The good thing is actually if you don't, enterokinase doesn't cleave it, so that protein still can bound, and then you elute it by imidazole. Then you collect it, you dialysis to remove the imidazole, and then concentrate a little bit, and then load it to the column again, and then load it to the enterokinase solution, and then cleave it again, and then do this, repeating this process. So now, another thing is, now you have, say, solutions with, now the solution is cleaved. So this cleaved histidine tag will bound to the resin. So you have a protein is here. But it's not finished yet, because you put, don't forget, you put enterokinase. This is also enzyme. So now it's still a mixture of your target protein and also enterokinase. So you get the enterokinase out, make the systems out. So this enterokinase is a bigger protein than compared to the size of the PYP. So you can do actually site exclusion chromatography that I explained, I think part 1 or part 2, that you can go back and see. So anyway, you can do site exclusion column chromatography of running about sodium chloride and then neutralize sodium phosphate solution. And you put the PYP. And then in this case, PYP is smaller. So then smaller protein eluted later. Bigger protein eluted faster. So then you take the faster eluted protein fraction, which indicating enterokinase, because you don't want that portion. You want the portion that has the later stage of the PYP. So then you have say monitor purity index as mentioned before, 280 divided by 446, and then you basically have showing this purity index very high fraction, which is later on this site exclusion chromatography. So that would be ended to this purification. So anyway, this all the procedure, anything that has columns in there, then proteins are diluted. Nickel NTA column, ion exchange column, and site exclusion column. Anyway, you basically dilute 100 times, 10 times, 100 times like this. So you have a very large volumes you end up with. So anyway, after this column step, you have to purify and concentrate again by the molecular code of either the PYP is about 14 kilodalton, 14 kilodalton. So that anything you can have a smaller membrane, then you use it and then you concentrate again. So this is the final concentration, and then this is the all the actual case study of how we actually applying the system that we learn about size, charge, affinity, and salt, that we combine all of them together and then purify this proteins from the E. coli. Okay, thank you very much.